Good morning, everybody. My name is Mike Miller, and the title of my talk is the Equilibration of neural propositions. So equilibration is a fancy word. It just means detecting and compensating for disturbances. And disturbance is basically a difference between what you expect and the actual outcome. So equilibration is a little bit of a big word, but it has a very big meaning. And my name is Mike Miller. Dr. Sheldon Linker and Dr. Piaget are also our co-authors of this paper. We're going to talk about interaction, equilibration, disturbances, and compensation. We're going to talk about the parent E2 system and equilibrium. So, according to Jean Piaget, to understand equilibration, we must first talk about systems and equilibrium. So, biological systems are both open and closed. Biological systems require external elements, for example, food, water, light, in the case of plants, that they exchange with the environment or the milieu. Here we can see some external elements and internal elements. Biological systems are closed because these exchanges form closed cycles of interaction between the system and the environment. Cognitive systems also are both open and closed. For cognitive systems, the external elements called observables by Jean Piaget correspond to information patterns in the environment. Stimuli, sensations, percepts, features, feedback from your senses, urges, and so forth. So let's look at how these observables are used by cognitive systems. We can imagine an agent. Suppose we want to build an intelligent agent, and we can build an agent from scratch, and we can use some patterns, some design patterns. So there's a few design patterns floating around. We can look at one of them. This particular pattern is called the reaction pattern. And basically, a cognitive system acts upon the world by selecting solutions for observed situations. So the cognitive agent has a device for its body, and it takes in percepts, sensory motor percepts, as observables. It has some kind of perception process or component or agent, which coalesces these into a context or a situation. And for this particular situation, or for each situation that it encounters, it may take an action. So it has solutions, a repertoire of solutions. These might be reflexes or habits. And some kind of solution selector picks one of these and says, go ahead and execute this in the world. And the executor component sends actions to the body to perform. And then it gets feedback in terms of more observables. And this cycle just continues. And this is a basic reaction pattern. Here, note that the processes are fixed, but the data, the observables, the perceptions, the solutions that are created, they vary over time. You can get into a little bit more sophisticated agent. This pattern is called the motivation pattern, where a cognitive system creates or reprioritizes intentions to ameliorate its urges. So we get observables, and observables include urges. Now, when we define the cognitive system, we define some what we call needs or homeostatic variables. And an urge is the delta between the target value of that homeostatic variable and the actual value. So for example, if we're talking about a cell phone, it may have needs for signal strength and power. And so those are the needs. And the urge would be the difference, the delta between what the target power, 100%, and the actual power is. So we get these urges in. And the perceiver forwards these urges to an attention module. And when the urge is not zero, it's not completely satisfied, it can create or form an intention to ameliorate this urge. So that's this particular pattern. And then the solution selector will say, okay, I have these intentions floating around, and I have the current situation. let me find some solution that may be applicable in this, or relevant to these intentions, or applicable to this situation to achieve the intention. We can take this one step further, and we have another pattern called the coping pattern. This is where a cognitive system creates or reprioritizes intentions based on its emotional state. So again, we have observables coming in, and the urges are propagated to the attention module, and the attention formulates and also reprioritizes the current intention. So if we have one urge for power, and another urge for signal strength, and the urge for signal strength is greater than the urge for power, the attention module will reprioritize the need for signal strength over the need for power. And then, so as the system progresses to achieve these intentions, we have some sort of evaluation process which looks at the progress of these intentions and appraises the progress. And these appraisals feed back into the attention. And if the system is making progress and has been relatively successful, it will continue to pursue these intentions. But if the system is not making very much progress, it may decide to abandon some of its intentions. And then the evaluator also is its beliefs about the world. So this is a pattern called coping. We have another pattern called deliberation, where the solver processes proposed solutions for intentions. So we need a way to bootstrap the system. And in the background, if there are no solutions that are relevant to a particular intention, the solver will, propose one, and then the solution selector can pick one of the proposed solutions if there are no reliable solutions that exist. So these cognitive system patterns can be used in architectures that form scheme-based models of the world. So what do you mean by scheme-based? So a scheme is a relationship or proposition or information pattern. And assimilation means basically just creating a scheme. And accommodation means cloning and modifying schemes. So we say observables can be assimilated into a cognitive system by creating corresponding schemes, which we call coordinations within the systems. So basically we have some information patterns that exist in the milieu, and we see our perceiver process will create a corresponding pattern internally in the system that mirrors the external pattern. And sometimes we can actually also just synthesize purely internal schemes. So for example, D is something we synthesize which has no external kernel. Observables and coordinations can both be assimilated into higher level coordinating schemes. So for example, the scheme enables V2 and V double prime C is formed by using the external element V double prime and the two internal schemes V2 and C. And we can form a higher level pattern. So we're just creating, synthesizing, constructing schemes. Schemes are accommodated by copying and modifying them. So when we start out with V2 and V double prime enables C, we can just clone that and change it slightly to say V2 and V double prime enable D. Or we can say V2 and V single prime enable C. So just to accommodate, for our purposes, just means to copy and modify. And to assimilate just means to create. So we talk about cycles of interaction. So a cycle of interaction is a functional dependency established among elements of the world and internal schemes. So biological and cognitive systems can form cycles of interaction with elements in the environment. So for example, given some observables and coordinations, so we have some external elements, external observables, A prime, B prime, all the way to Z prime, and some internal coordinations, A, B, and C, all the way to Z. The cognitive system can assimilate them all into higher level coordinating schemes, such that the observables activate the coordinations. So in this case, we have A and A prime enable B, B and B prime enable C, all the way through to Z and Z prime enable A. As the activations chain, cycles of interaction form. When the final observables, for example, Z prime, activate the initial coordinations, for example, A. So this was very important to be able to have the external elements activate internal elements, and then have these activations chain and form these cycles of interaction. So as the cycles of interaction stabilize and become predictable, the system is said to be in equilibrium with the environment. So when you perceive some object in the world and your mental, your internal schemes are activated by those objects, and we can be said to be in equilibrium as these cycles become predictable and stabilized. When a cycle is broken because of a missing or newly introduced observable, the cycle is what we call disturbed, and it can either be abandoned or evolved. So, for example, when the external element B prime doesn't appear, goes away and is substituted by an element B double prime, that particular cycle is broken. And we can either abandon the cycle or evolve the cycle. To evolve the cycle, the system must adapt the disturbance by detecting that disturbance, and then the system can compensate for the disturbance, possibly by saying, okay, we don't see B prime anymore, but we can use the B double prime, and we can synthesize a new internal element B2, and we can form a new scheme that will enable C. So this is, for example, when you have a concept, and it's not quite exactly what you thought it was, but you can synthesize something else to activate that concept, so that the interaction cycle can be restored, thereby creating a better and more stable cycle. So this is an example of equilibration that restores and evolves a cycle of activated propositions. At higher levels, equilibrations may evolve hypotheses to improve predictions or evolve solutions to achieve intentions. So equilibration means detecting and compensating for disturbances. And to compensate means to exert an opposite force or effect. And a disturbance is basically a discrepancy, a difference, a conflict, a contradiction between our expectations and the actual outcomes. So we gathered some requirements from a book called The Development of Thought by Jean Piaget. There are two translations from 1977 and 1985. And we have a new pattern to add to our agent. And this pattern is called the compensation pattern. And basically, action outcomes are correlated with expectations to detect disturbances, which drive regulation and compensation processes that adapt solutions and intentions. So basically, the body, we take an action, and the body tells us, or the device tells us, whether or not that action succeeded or failed. That's an outcome. And we take in that along with our observables. Our perceiver creates the context, the situation, and the solution selector picks a solution that addresses our intentions and relates to the context. But when it picks that solution, it actually applies the solution and creates a forward situation or forward context. And we save that forward context as an expectation. We expect that if we take this action, we apply the solution, or we do the solution, this will be our future outcome. And then it correlates that expected outcome with the actual outcomes. And it passes that information on as a disturbance. And then the disturbance will go through regulation and compensation processes. So regulation means to correct or reinforce, in this case, a solution. And then the compensation means to invert or to choose or to eliminate the intentions. So we'll see a little bit more how that goes. So we're talking about equilibration. So an equilibrative system needs to have a world, real or virtual, in which it resides, a body or a device able to perceive and act in the world, a knowledge representation for percepts, the observables and inferences with coordinations, the ability to create, copy, or modify the represented knowledge, and a disturbance detection process, and a regulation and compensation process. So the disturbances are caused by unforeseen obstacles. These are changes in the world, or maybe we can only partially observe the world. And they're also caused by knowledge gaps, having an incomplete model of the world, which the model is never complete, generally. The disturbance types that we look at are failed predictions, failed solutions, and unsatisfied urges. The failed prediction, basically we have a prediction proposition, which has a hypothesis, beginning and end time frame, and an outcome. Our hypothesis has preconditions, postconditions, some basis, whether it's empirical or logical, and time frame. And an example, we say, given a prediction P, and a hypothesis H, which is related to P, for its outcome, if its outcome is expired or failure, then we do some kind of compensation. Similarly, for solutions, we try a solution for a particular time frame, and we record the outcome. This is a try proposition. And our solution has preconditions, maintenance conditions, prohibition conditions, some steps, and post conditions. And then some time frame, and we say, given this attempt, this try at a solution, if the outcome was expired or failure, then we perform some kind of compensation. And similarly for urges, we say we have a need and an urge related to the need, and if the urgency or the delta is greater than 0, then we perform some kind of compensation. So once we detect a disturbance, we have 3 options. We can ignore or reject the disturbance, we can incorporate or transform it. So ignoring a disturbance means maybe we try an alternative instead of addressing this particular disturbance head on. Or we perform some other processing, or we reinterpret the disturbance, thereby deforming the disturbance. Or simply, maybe we do nothing about the disturbance and just keep going. That one was called an alpha reaction. Piaget refers to it as an alpha reaction. We may be able to incorporate disturbance. So this means assimilating the disturbance by making it a predictable variation. We create an exception, and we maintain that exception in our system. And this is called reciprocity. And then and it usually occurs through regulation, where we reinforce a success or correct a failure. And reinforcing success, Piaget calls this compensation by filling in knowledge gaps. And correcting failures, he calls it compensation by synthesizing reactions. So we synthesize the negative amount. This is a beta reaction. And finally, we can transform the compensation by creating operations that cancel or reverse the disturbance, by incorporating the disturbance into the operation. And basically, if we can cancel undesired side effects or reverse action statements. So the classic explanation is if we're riding a bicycle and we notice our balance is shifting, we can reverse or invert by shifting our balance in the opposite direction to cancel the undesired side effect. This is a gamma reaction. So the system that we're working on is called PAMP2. It's the Piagetian Autonomous Modeler. It's written in the premise language. It uses what I call neural propositions for its knowledge representation. We saw a few examples of those just now. It has 4 major categories of agent processes: observation, which are mind-device interfaces processes; coordination, which are inferencing processes; reflection, which is metacognition, and consolidation, which is forgetting and authenticity. It has a global shared persistent memory, and so there's no long-term or short-term memory distinction. And it's comprised of cognitive system patterns like the ones we saw. Mind-body pattern, basically taking information, exchanging information with the device, which is the body. Observation, which is storing information. Coordination, which is making inferences. Reminding, reaction, deliberation, motivation. Simulation, which is daydreaming. Compensation, and coping. And when you put all those patterns together, you get something that kind of looks like this, where the ovals are propositions, and the squares are the agent processes, which consume or produce these propositions. Yeah, a little faster. So agents assimilate and accommodate neural propositions. Neural proposition kind of looks like this. It has terms, it has a body, which is the scheme, and it has reifiers. It comprises of supporting propositions, a viewpoint, which is reasoning context, activation, belief, which is statistical attributes, which form a causal interpretation, monads, which are the affirmation and negation reifiers, and a scheme, which connects the proposition to the support structure. And the main proposition can be anything: solution, hypothesis, action, episodes. This sort of looks like this, where you have the main proposition, the scheme points to it. It has the positive thesis, or the affirmative version, the antithesis, which is the negative version, negative perspective. And then it has activation in the future, present, and past, 10 dimensions, and then beliefs associated with it, all within a reasoning context. The premise language is this: JavaScript, ops, production system, and some object relational management combined. We have premises, which kind of look like this. You have a prototype, an identifier, slot values. You have functions, which look like list of functions. Sample agent and premise looks like this, where you have a prototype and the function for the agent job. So it can be two agents that detect disturbances. We have prediction correlators, try correlators, attempt correlators, and an attempter, which converts urges to canceling intentions. We have agents that compensate for disturbances, which, for example, solution regulator, solution compensator, hypothesis regulator, evaluator, which appraises the intention progress and updates beliefs, and the attention agent, which creates or modifies intentions to achieve problem or emotion-focused coping. Regulation, basically, we have successful solutions or predictions. We increase their utility and reliability. We randomly recombine them, and we identify or accommodate serendipities. It's when you achieve your goal, but you've not finished executing your solution. So you serendipitously achieve your intention. And failed solutions or predictions, we decrease their utility. We accommodate them by extending the time frames, allow a little bit more time if they expired early. And we accommodate and ascribe failure clauses, and accommodate and ascribe undesired side effects. Compensation, we construct new solutions with reverse actions to allow us to invert. We create intentions to eliminate undesired side effects. And we prioritize, suspend, resume, abandon open intentions based on appraisals, affect, mood, and equilibrium to achieve emotion-focused coping. So problem-focused coping is when you create an intention to achieve a goal. Emotion-focused coping is when you modify your agenda based on the progress. So finally, equilibria is having accurate hypotheses and solutions and having satisfied needs. And equilibrium is only ever temporarily maintained because new equilibria always open onto new problems and potential operations. So the entire process is a continual becoming, since new disturbances will necessitate further compensation. That's it.
Excellent.
any questions?
Have you applied this to any application in particular, or just?
So we're working on getting a robot. We have a now robot, and getting the robot to transmit these observables into our system and our system to control the robot. That's still the process.
Would you go into further detail on how to set the target value for your homeostatic variables?
Yeah. So when you create some software to run on your device. We call it psyche software. You know, it's a soul that's acting on your device. And in that software, the software is geared to the specific device. So you're going to specify two things. You're going to specify a set of actions that are the device can take, and then a set of needs or homeostatic variables. And for those needs, we generally say that we just generally give a list of what the needs are. We really don't care because the computer system is agnostic to all the devices. And when you send, when the psyche software sends the observables, it'll send an urge message, and you just start from 0, and you increase the urge depending upon whatever range you have preset. So, you know, if you scale your power up 1 to 100 or 1,000, doesn't matter. You know, you just send the delta as the urgency, and then the system should just recognize that you have a particular need with a particular urgency, and then perform calls to adjust that. So the range doesn't matter. Kind of those things back to. Question?
What are some of the larger systems you've been able to simulate working together?
So it's still in development. So, actually, it's good that you asked that. What happens is, on the lowest level, you have observables activating coordinations, which we saw earlier. And then on a higher level, you form action sequences and reaction cycles. And then you can form circular reactions, like we had circular activation. And where the final action stimulates the initial action. And then you have primary, secondary, and tertiary circular reactions. So primary circular reaction is where the system just performs actions randomly to ascertain what the effects are, and this basically constructs the model. When you then, after a point, it can use the action chains deliberately to achieve effects. And this, now we're using the model. And this happens in infants, And then finally, the system can perform actions experimentally to refine the model, to differentiate the effects. And then at an even higher level, you can engage in play and imitation. And play is interaction cycles having more assimilation than accommodation. And imitation is interaction cycles having more accommodation than assimilation. So you're imitating, you're copying what is in the world as opposed to just building your own. And then the ultimate goal is to get from just basic interaction cycles into play and imitation. And then at higher levels, you have symbolic play, creative imagination, preconception, and expert.